ends up looking like for a reaction is that when you have a lot of the reactants, the chemical potential increases, it's very high. And when you have a lot of the products, the chemical potential increases, and it's very high. And as those reactants go to products or products go to reactants, there's some minimum that is reached. And the slope of that curve, however that curve ends up looking, the slope is the change in the chemical potential with respect to the composition of the solution. Delta mu versus, or delta G versus N. How much does the Gibbs free energy change per mole of species? And so essentially, the slope of that curve is the delta mu of the reaction. And you can see that when that slope is negative, we're moving down, and the reaction moves from the reactants towards the products. When that slope is positive, the reaction moves from the products back to the reactants. And so we're already kind of getting, or by looking at that, we're getting what we already knew, which was that a negative delta G is a spontaneous reaction. It moves from reactants to products spontaneously. And that a positive delta G, a positive slope when we're on the product side, moves spontaneously from the products towards the reactants. It moves backwards, right? So it's a non-spontaneous reaction unless we write it in a reverse direction. So now we're going to just take some time and meticulously write out what the total delta mu is for an arbitrary reaction. We're choosing a reaction right now where A molecules and B molecules go on to form C molecules and D molecules. We could have written this any way we wanted. We could have had a 2-component reaction. We've got a 4-component reaction. We could have done bigger. It doesn't matter. Assuming that we've got this A and B molecules goes to C and D molecules, then the delta mu is equal to the mu of the products minus the mu of the reactants. And each product, the little b's or the little letters are the stoichiometric coefficients, so we can put those outside and multiply each individual chemical potential by the stoichiometric coefficient. So we've got coefficients times the chemical potential of the species, where the chemical potential of the species is mu naught plus RT line activity. Writing that out, we can group all of the terms that regard mu naught, and we get this term, that's just delta mu naught. So delta mu at the standard concentrations or pressures or whatever it is, plus this RT natural log of this guy right here, activities raised to the powers of their coefficients. And that should look very familiar to you because we've all worked with equilibrium constants. We already know where this is going. And we're familiar with the equilibrium constant being a function of the concentrations of a species raised to the power of its coefficients. Well, that's where this comes from. In those equations that you looked at, the concentrations were the activities. So we had a solution where it behaved correctly so that we could use concentration as the activity. In this case, we're just writing out the generic expression where we're not sure whether or not we can use concentration or pressures. And so we're just writing activity raised to the power of its coefficients. All that this equation comes from, though, is writing out the chemical potential of each species and knowing how that chemical potential varies with pressure or concentration or activity, right? So you write out the total chemical potentials, you subtract reactants from products, and you get that big expression that says that delta mu is delta mu naught plus RT times the natural log of this thing, which we already know is going to be called Q. So when it's not at equilibrium, it's called Q. When it's at equilibrium, it's called K, the equilibrium constant. And one of the things that this tells us is that something I wanted to stop and just comment on for a second is that a reaction where delta mu naught is negative will tend to be spontaneous. The negative sign here will contribute to a negative sign overall. But and this we'll see ends up being kind of dominated by, well, it's delta mu naught as a function of delta H and T delta S. When you have a negative delta H, when you have a reaction that's releasing heat, it tends to be spontaneous. Even if this isn't negative, even if it's positive, we can still make a reaction favorable simply by adjusting the activities or the concentrations. Activities go as concentrations. The larger the concentration, the larger the activities are. We can make a reaction spontaneous by putting enough of the products in there. So even if we have a reaction that doesn't tend to be spontaneous just based on the relative chemical potentials of the reactants and products, simply adding enough of the reactants, put a large number down here, that RT natural log thing becomes a negative sign. You make that large enough, then you can outweigh that delta mu. So I think that's all I want to say about that. Yeah, and so that this expression relates to that curve that we just showed you a second ago, the chemical potential versus composition curve and the slopes of that curve. And we know that if concentration of the products are high, if the concentrations of the products are high, then it puts the value of delta mu towards positive. And so then we're on this side of that mu versus composition curve. At a high amount of components C and D, we're moving towards the products and we've got a positive delta mu. And at a low amount of C and D and a relatively high amount of A and B, we're on the product side of that curve, the reactant side of that curve, and we've got a negative slope on that delta mu, okay, on the mu versus composition curve. So that equation basically tells us how to calculate the value of that slope that we were looking at just a second ago. Yeah, and so I think that's what I just said, so I won't say it twice. You can go back and reread the notes. So we give this thing a name. We call it the reaction quotient Q. And you might guess that I'm going to tell you right now that at equilibrium, we give it a different name, and it is called K. So let's go there right now. We know that for a reaction at equilibrium, delta G is 0. And so we can write this guy out. We can say delta G is delta G naught plus RT natural log of Q, setting that equal to 0. We get an expression that says that delta G naught is equal to negative RT natural log of Q. Natural log of Q then is equal to negative delta G over RT. And that's Q of equilibrium, which we're going to call K. And so K, the reaction quotient at equilibrium, is equal to e to the negative delta G naught over RT. You'll notice that if delta G of the reaction is negative, K is going to be greater than 1. This is all repetitive. We're all just saying the same thing a million different ways. If delta G is negative for the reaction, K is greater than 1, meaning that there are more products than there are reactants, which is what we expect. Okay? For spontaneous reaction, we expect there to be more products than reactants. And if delta G is positive, then that's a negative on that exponential, and so K is going to be less than 1. So a reaction that has a positive delta G doesn't proceed spontaneously, and so there are more products than reactants. So K is going to be less than 1 if delta G is positive. an important thought. How do the magnitudes of delta H and delta S affect the spontaneity of a reaction? We know that delta G has to be negative. And so if we have a negative delta H, that's going to tend to make the reaction spontaneous, right? Negative contribution to the delta G tends to make the reaction spontaneous. Why? What does a negative delta H tell us? What does that tell us is happening?
It's exothermic.
It's exothermic, right? What was the original equation that we wrote to express the tendency of a reaction to be spontaneous? What was it a function of? When we originally derived the delta G equation, what were the principal things that we were interested in? Entropy. Right? We said that the entropy of the universe had to be increasing. So delta S of the system and delta S of the surroundings, the sum of those had to be greater than 0. If delta H is negative, whose entropy is increasing?
Surroundings.
Surrounding. A negative delta H means that heat is being dumped from the system into the surroundings. And so if delta H is negative, you know that the entropy of the surroundings are increasing, right? Delta S is delta S of the system. If that's positive, then what's happening?
It's entering the system.
Entropy of the system is increasing. And so a positive delta S tends to make delta G negative. A negative delta H tends to make delta G negative. Basically, we're saying that things that lead to an increase in entropy lead to a favorable reaction. Delta G is going to be favorable if the entropy of the unit or system is increasing, and it's going to be negative if the entropy of the surroundings is negative, or is increasing. Sorry, not negative. Sometimes I say things that are not what I meant to say. I apologize. Okay, so if the surroundings entropy is increasing, delta G tends to be negative. If the system's entropy is increasing, delta G tends to be negative. And you can play with this equation, delta G is delta H minus T delta S, a million different ways. I wrote a little bit about that. If you have a positive delta H, so the system is absorbing heat from surroundings, so the surroundings entropy is decreasing, that tends to make things unfavorable, but that doesn't necessarily mean that you can't have a spontaneous reaction. If the magnitude of T delta S is large enough to overcome a effect from the delta H that moves us away from spontaneity, if the magnitude of T delta S is large enough, we can overcome that effect and drive the reaction towards spontaneity. So a reaction that has a positive delta H but a very large T delta S will also be spontaneous. Can be spontaneous. You increase temperature, you raise the temperature of the reaction, that raises the magnitude of T delta S. Obviously, if you raise delta S, that raises the magnitude of T delta S. So there are a couple of, and you can draw that any way you want. Make delta S negative, you've got a positive contribution from the T delta S, moving you away from spontaneity. Well, then if you have a negative delta H, you can move towards spontaneity. There's a million different scenarios, and your book has a little chart that kind of itemizes the different scenarios that you might see based on the relative signs of delta H and delta X. All right, now it's study hall time. So you guys have seen these problems a million times. It might take a little bit to remember it, but we're gonna throw an equation at you. Nitrogen. This is actually one that's in your book, so you can do your work now. And go back and check your work in the book. We've got nitrogen gas reacting with hydrogen gas to form 2 molecules of ammonia gas. I've given you the delta G knots of nitrogen, hydrogen, and ammonia. And I'm leaving it to you to figure out what the equilibrium pressures will be of a reaction if you start off with nitrogen at 1 bar and hydrogen at 3 bars, temperature at 574.8 Kelvin. And we're gonna say that these gases are behaving ideally, and so we can substitute the pressures in for the activities. So you're gonna have an equation for delta G that's in terms of the pressures raised to the powers of their coefficients. You'll calculate a K first. Once you've calculated a K, you're gonna write out your expression for your equilibrium constant, and you'll use an ice table to show what changes happen, and you'll end up with an expression in terms of X for your ice table. All right, go for it. I know it's not that hard, but I gotta give you something.
Write down the equation.
Delta G naught. The equivalent expression for K is natural log of K is equal to negative delta G naught over RT.